Support Moof University and the production of more video tutorials by making a financial contribution or by getting yourself one of these t-shirts. Details under the Support Moof section of moofuniversity.com. The link will be in the description below. Thank you and enjoy.
So earlier we mentioned that chemistry was the study of matter and the way that matter changes. So when we're talking about matter, there are some laws that we need to take into account. First one being the law of mass conservation, sometimes mentioned as the law of conservation of mass. And so before we get into what it is, let's think about who stated this law. It was this French dude named Antoine Lavoisier. I think that's how you pronounce it. If you're French and you think that was horrible, I'm sorry. But anyway, he's the one who stated this law, and it was based on his experiments with combustion. He had some combustion experiments that he was working on, and he stated this law based on that. So what does the law actually say? It basically says that during a chemical reaction, which is actually pretty important there, during a chemical reaction, the total mass of the substances does not change. Okay, and there are some key words I want to highlight. Okay, during a chemical reaction, okay, the total mass, of course, does not change. Right, does not change. Okay, so what does that really mean? Right, that's the question here, and it's really just best explained with an example, at least in my opinion. So if we look down here, we got three different general reactions here. The first one where we have some compound or substance A and some substance B that we're adding together, and they are reacting, hence they're called the reactants. Because they are reacting together, and they're giving the products, right? The things that we're producing in this reaction, products C and D, which are two separate substances. Okay. So what does the law say according to this reaction? Is this a chemical reaction? Yes, it's a chemical reaction. The total mass of the substances does not change. What that basically means is that if we think about the mass of A, which I'm going to label here as mass subscript or M subscript A, if we take the mass of A and we add it to the mass of B, whatever that is, that's going to equal the mass of C plus the mass of D. So let's just say that the mass of A plus the mass of B just happen to be equal to 50 grams. This reaction will occur between A and B to give us the products C and D, and then we'll be left with only C and D. The mass of C plus the mass of D will also equal 50 grams. That 50 grams that we started with is the 50 grams is still there as 50 grams, even though it's just in a different form, right? So that's one example. Same idea here. If the mass of A plus the mass of B equals 50 grams, maybe they don't give us two different products. Maybe it just gives us one, right? In this reaction here, we get this product E. That would just mean that if E is all that's left over at the end of this reaction, then the mass of E will be equal to whatever mass we started with. If it was 50 grams initially, then we'll have 50 grams here. Okay. Same idea here. If the mass of A was 50 grams, now of course it doesn't have to be 50 grams, right? It can be any amount of mass. But if this A decomposes into F and G, then that means that the masses here will add up to be equal to whatever we started with. Okay. Now these are all general ideas. Now let's think about a real life example. This here is the combustion of methane. It's the combustion of methane, and it is a chemical reaction. So we have methane, which is a CH4 here. It's oxygen. There's a combustion, basically, and we get carbon dioxide and water. And so I'm not going to go into all the details, but let's just say this. Let me just propose a scenario. Let's say we had 16 grams of methane and 64 grams of oxygen react, and then we ended up with 44 grams of carbon dioxide and 36 grams of water. Does this obey the law of mass conservation? Well, I mentioned that it was a chemical reaction, so it has to, right? 16 grams plus 64 grams, that of course equals 80 grams, right? And then 44 grams plus 36 grams also equals 80 grams. So these two values are equal. right? So mass was conserved here. So really, what's the idea here? I keep really saying it over and over, but it's the idea that the mass of the reactants must equal the mass of the products. That's really what this law says, right? Sometimes it's commonly stated as matter is conserved or mass is conserved. I've seen both being said. It's also commonly mentioned as matter can, or it's commonly stated as matter can be, or excuse me, cannot be created or destroyed. Matter cannot be created or destroyed. It can only change form, right? So we had, in this first example up here, we had this 50 grams of matter in the form of A and B. And during the course of the reaction, at the end of the reaction, we have that same amount of matter, right? Same mass, right? Same amount of mass, just in different forms, right? In the form of C and D. Another question that's important to ask is, are there any exceptions? Are there any exceptions to the idea of mass conservation? And maybe you've guessed the answer is yes, just because I wrote the question down. And that would be a good guess. The answer is yes. There is an exception to the idea of mass conservation, and that's something we'll talk about later, specifically with nuclear reactions. Okay, and so that does not obey the law of mass conservation. We'll talk more about this later. Mass changes in these reactions, so that's pretty crazy. But anyway, I hope that video was helpful. It's a quick intro to this concept. Thank you for watching.
Don't forget to hit that video with a like if you found it helpful or enjoyed it, and be sure to share it with anyone else who you think might find it helpful. Also, if you'd like to support the channel, follow Moof University on the different social media links, Twitter, Facebook, all that stuff, links in the description below. Thanks, and happy studying.